Where there is lightning, there is thunder. Static electricity makes lightning, and AC/DC brings the thunder. First off, make sure you have in your notes the fundamental law of electric charges. If we have two opposite charges, one plus, one minus, they attract. If I have one minus, they repel. One positive, they repel. The neutral one, make sure you know that if you have a negative charge and you put it next to a conductor that is neutral, all of the opposite charge will come close. All the same charge will get farther away, and so these will be closer, so the attraction will be bigger than the repulsion, and so they'll attract. So if you have a conductor, then a neutral object can be attracted to a charged object. It can be negative or positive. Yeah, make sure you know that. That's kind of new. Conductor, charge can move. Insulator, charge does not move. Both can be charged. You can put positive charge on either one. If you put a positive charge on a conductor, since it can move, it all goes to the very outside of the conductor. If you put a positive charge on an insulator, it all just stays right where you put it. Now it may drift a tiny bit, but it's not going to move as quickly as it does in a conductor. Conductors let charge move wherever they want to go. Insulators do not. 3 ways to charge an object. We can first of all touch two objects together. If one likes its electrons and one hates its electrons, this one will give away its electrons to be positive. This one will take the electrons to become negative. So two objects touch, they start neutral, but this one gives that one its negatives, leaving positives over here. That's molecular contact. And a lot of times it looks like friction because you want to touch as many times as possible. We look on the electrostatic series, that's the page on your book to get it, and I have a copy of it right after this, to see which one becomes positive and which comes to be negative. If you have an object that is really positive and you touch it to an object that is negative with a wire or by just touching it, it shares its charge. So then each of them will be positive, but less positive than the first one was. What happens is they equalize the charge density on the surface, so they get as far away from each other as possible. So if you have a really big object over here, it'll have more of the charge. Small objects will have less because the density of the charge on the surface has to be the same, and that's what it's going to equalize. The last one is charging by induction. Charging by induction is very similar to the neutral objects. Let me get another picture. For charging by induction, I take a really positive object, this one, move it close to a neutral object, and then I put a ground. That's my symbol for a ground. Remember, a ground is an infinite source of positives and negatives. On the neutral object. All the positives that are in this leave because they're repelled by this, so those leave, and negatives come up to take their place. If I was to take away my positive object without taking away the ground would neutralize these. But if instead I leave the positive there, get rid of the ground, and then get rid of the positive, I'm left with a net negative charge. So charging by induction always gives me the opposite charge of whatever charge you bring it close. So I brought it close to this positive over here, and that makes a negative because essentially I put the ground on, all the positives leave, I take the ground off so that it can't neutralize itself. If I ever have a charged object by itself and I put a ground on it, a bunch of positives will come up and neutralize that. So I have to make sure I take away the ground before I take away my positive charge if I want to charge it by induction. This is my electrostatic series, and it tells me which elements or compounds really like to keep their electrons. Things that are towards the bottom like their electrons. Things towards the top like to give away their electrons, so I put a plus up there. And so if I rub rabbit fur with saran wrap, I know that the saran wrap is going to be negative because it's close to the negative. My rabbit fur is going to be positive because it's close to the positive. It's a relative thing, though, because if I take saran wrap and rub it with Teflon, saran wrap is then closer to the plus, so then the saran wrap would be plus and the Teflon would be minus. So there's a lot of different levels of really liking your electrons, and you kind of have to look at what substances you have to see which one's plus and which one's minus. Notice this explains something about saran wrap. Notice saran wrap it was designed when all of our containers were glass. So if you touch saran wrap to glass, one becomes positive, one becomes negative, and they attract each other. So your saran wrap stays on there. Works really well for glass. However, when we get to Tupperware, which is polyethylene or polypropylene, one of those in there, very close to saran wrap, so those aren't going to stick as well. So if you have saran wrap and you put it on plastic, it doesn't work as well. It doesn't work on plastic. Use it on glass, and then it'll work really great. Physics knows all. Man, I'm really hungry today. I have to admit I've been snacking before I was supposed to snack. Today's snack is cheese and crackers. Pretty much a classic. This time I'm going with Nut Thins. Nut Thins are almond crackers that are just really good and crispy, and I put brie on them. Brie is kind of a weird cheese. It's got this white stuff all over the outside of it, so people get a little freaked out, but it's awesome. Here's what it looks like when you get it. It comes in a big puck, and so people get freaked out because it's all weird looking. Can you see that? Yeah, that's how it's supposed to look. It's really yummy. I had to fight my son off. He wanted to eat it. Thanks for giving me a video because I get to eat the brie. Okay, so we know that charges are attracted or repelled, but we have a formula that'll tell us how much. So we have a force formula. Now this force formula is going to go on a free body diagram like every other force we have. We know it can be present with other kinds of forces like gravity. My formula is K, which is a constant, 9 times 10 to the 9th, times each of the two charges in coulombs, which is how we measure charge, divided by the distance between the charges, between the middle of the charges, squared. Notice this looks a whole lot like our gravity formula. And there's a reason for that. We'll talk about that later. It's a vector, so we know that by the fundamental law, we have to find the direction. So if one's positive, they repel. So if this is the one I care about, it's going to go in that direction. So when I'm doing charges, let's say this is 1 coulomb plus this is 3 coulombs, and they're 2 meters apart. I just plug it in the formula. So I go 9 times 10 to the 9th. Notice that's a pretty big number. My gravity number was small. Electricity is a much bigger force. I take 9 times 10 to the 9th times 1 coulomb times 3 coulombs divided by 2 meters squared, and I got my force. If I'm looking at the force on this one, that's gonna repel, it'll be the right. But if they ask me for the force on this one instead, it'll be the left. So you have to know which charge it is you're looking at the force on. There'll be equal and opposite forces, the same number. One goes one way, one goes the other way. And you have to add them as vectors with any other forces that are present. If we have a place in space, like this place right here, and we know we're going to put a whole bunch of different charges right there, we want to find the force quickly, we find what's called the electric field. The electric field is everything that's in the force equation except for one of the Q's. And so it's KQ over R squared, like you'd only have this one charge, like 5 coulombs, to a place that is 2 meters away. You plug in the K, the Q, and the R squared. That electric field is everything except for whatever charge you're going to put there. So you can put a lot of different charges there and find the force easily, because then the force is just going to be my electric field times Q, whatever Q I put there. Now notice, this is exactly what we did with gravity. When we wanted to find the gravity on Earth, we found everything that's in my big G formula, the Fg equals gm1m2 over r squared, except for one of the masses, and that all became 9.8. So the electric field is the 9.8 equivalent for electricity. Here's a quick chart showing that. We have electrostatic forces on gravitational forces on this side, electrostatic forces. Notice this equation looks a lot like that equation. One difference is that gravity is small and electrostatic is very, very large. Both are inverse square, which means that it's proportional to r squared on the bottom down there. Electrostatic is different in that I have both attractive and repulsive, and gravity is only attractive that we know of so far. We can find gravitational field strength G the same way we can find the electric field E in electrostatic forces, and there's equivalent equations here. F equals mg, F equals QE, Q being the equivalent of mass for charges. That leaves everything else in that equation for G and E. Now, when we're doing gravity, we only really did it at the surface of the Earth, but we could have found it at a bunch of different places that were farther out. You can find the equivalent gravity out in space. We usually only did the one at the surface of the Earth. For electric field, we find it at a lot of different places. Just like gravity is newtons divided by kilograms, the electric field is newtons per coulomb. And the direction's a little bit different. For gravity, I always go towards the center. For positive charges, I'm always going to go away because 2 pluses will repel. To help me visualize electric field, I like to make what's called electric field lines. And they're little arrows that come away from any charge. And what they do is they show the way that a positive charge would move. So if I put a plus right here, that's a plus right next to it. They're going to repel, so it's going to go in that direction. So I draw my arrow in that direction. If I put a plus right here, it's going to be attracted to that negative. So all my lines go towards negative and away from positive. If just the positive or negative is there, it's pretty easy. When you get both of the things there, you start getting weird curvy bits in certain areas. They always have to be perpendicular to any conductor, as a rule, just because of the way conductors work. And then they're closer together, like if they're close to this, somewhere in here, my lines are closer together, I have a stronger electric field. When they get farther away from each other, like out here, that's pretty far apart, that means that my electric field is weaker. And if I wanted to find it at a certain point, like if I want to know what the electric field was right there, I'd take a tangent to my electric field line. That's the way the electric field would be if I wanted it right there. Inside a conductor, my electric field has to be 0, because if it's not 0, then it would move all the charges until it was 0. And so, as a rule, no electric field inside of a conductor. And if I ever get, well, we'll talk about this one a little later, actually. There's actually 2 ways of visualizing electric field. The first way I just showed you is this one. It's the more common usage, but your AP test likes to give you vector fields, which is this other way. And it puts actual arrows, a lot of different arrows, showing the relative strength. So it's going to say that since this arrow is really big, you have a big electric field there. As you get farther away, my arrow gets smaller and smaller. You can see that they're pretty equivalent. But this one maybe has a little bit more information and showing you the magnitude of the electric field at all those different places. This one you have to assume that based on how close the lines are. This is the one that's actually on your test. But this is the one used more commonly in physics. One last thing before I let you go do a bunch of force equations and electric field equations. That is that we have a lot of KQR equations for electricity. And so we have this nice little chart here. So far we've only done these 2, electric field and electric force. And notice that the only difference between those is a Q. So I'm going down that, I would add a Q to electric field to get the force. We're going to get energy and we're going to get potential later. But notice they all have K's and Q's and R's. I'd like you to get this into your notes now. And we'll talk about these 2 next time. AC, DC. 2 kinds of electricity. DC is what we're doing now. We'll talk a tiny bit about AC in a bit. Always a good band. You are ready now. You know the force part and the electric field part of electricity. We'll get the energy and the other parts in a bit. It's time for some quests. Good luck.